Hey, wonderful. Thank you very much. My name is Matthew Gallus, and I'm the vice chair of the AIAA Hampton Road section. So we are kicking off with Dr. Laura Titolo. Did I pronounce it correctly?
Yes.
Our technical talk series. She's a senior research scientist at the National Institute of Aerospace, and she's working in safety critical avionics systems branch here at NASA Langley. Should I go further? Or? Okay, so.
No, I mean, as you wish.
Okay. I'm really excited about this talk. She gave this presentation for the research directorate previously, and I think it's a wonderful talk. So I'm very happy that she accepted our invitation to come join us. Thank you very much.
Thank you, Matthew, for the nice introduction. Okay. So do you all see the screen, right? Okay. So yes, in this presentation, which is like an overview of the work that we have been doing in the past few years that concern the analysis of numerical errors in safety critical avionics applications. So this is a joint work with my colleagues from both NIA and NASA Langley. So they're Mariano Moscato, Marco Feliu, Aaron Dato, Paolo Masci, and Cesar Munoz. Okay. Okay, yeah. Okay, yeah, now it's working. Okay, so yeah, we have been working mostly on analyzing what happened when we implement our software using floating point numbers. So you all know probably that floating point numbers is a very common finite representation of real numbers in our computer and in our software. So being a finite precision representation of reals, it is true that not every real number can be perfectly represented as a floating point. So, for example, we have an uneven distribution of floating point in the real line. So we will have more floating point when we are very close to zero, and then the gap between one floating point and the following one will become bigger and bigger as far we are going from zero toward the infinity. So what happened then? When we have a real number that falls in this gap between two floating point numbers, we have to round it. And normally we round it to the nearest floating point number to minimize the rounding error. But we will still have a difference between what we have in our mind ideally and what it is in fact represented in our computer. So this rounding error or representation error will propagate when we write a computer program and when we do our computation. So for example, if we write a program and we have some expression and something else, this error propagates and they become bigger and bigger. So let me just show you a very simple motivating examples, and this is a real computation that I did in my computer using an interpreter. So using double precision floating point number. So we'll have this 4 divided by 3 minus 1, multiply everything by 3, and then rest had minus 1. So this, of course, if we do your calculus, is going to be 0 when we evaluate it in real arithmetic. But when we evaluate it with double precision floating point arithmetic, we will get this very small number, which is very close to 0, but of course it's not 0, is something on the order of the 10 at the minus 16. So this may look like a very small and error, and it's something, okay, we can live with that, it's small, right? However, if we apply an operation such as the floor operation to this number, we get the minus 1 result. So here we will have already a difference of 1 unit between the floating point computation and the exact real number 1. And this is something that's already a bigger divergence. And furthermore, if we assume that we have an if then else, and we are checking, for example, if the floor of this expression there is negative, then we return 100. Otherwise, we return, for example, 1. Then this computation will return 100 in floating point arithmetic. But it should have returned 1 in real arithmetic. So we will have a round of error of approximate of 99 units, which is already very big, and we want to avoid this kind of situation. So we want to limit the floating point errors, or we want to detect when they happen, and we want to know how big they are. So of course, right, like as I show you here, you can already see that writing floating point code can be challenging. So we already have some very well-known problems, such as the runtime exception. For example, when we divide by 0, when we have overflows, etc. Besides, while these runtime exceptions are detected by our computer, so we will get a notification when something like that happens, round of errors are not like this. So we're still getting a number, and we have no idea if that number corresponds to what we would expect with real ideal real number arithmetic or not. So we have found several examples of floating point errors that make software fail, and one very famous example is the Patriot missile failure in 1991. So this, in fact, was due to an accumulation of rounding error that became so big that the technology wasn't able to detect a missile coming in. And in addition, we have found other examples that I will show you here. So for example, when we have a floating point computation that accumulates a very big error, we can get a problem in geofencing application for unmanned aerial vehicle. For example, imagine that this is a red one is a geofence, so it's some place where the drone cannot enter, and so we want to avoid it. And we have that with real value arithmetic, we detected the drone is inside and it violates the geofence. However, with floating point computation, due to the accumulation of round of error, we may have that the program still say that the drone is outside the geofence, so everything is fine. So this is one problem that we have detected in some software. And also we have this kind of error in detect and avoid system to coordinate the maneuver of an aircraft when, for example, we have one airplane and the other one that are heading toward each other, so they have to coordinate a maneuver. So both turn right and both turn left. So if we have some floating point errors, one airplane may make the incorrect decision and turn in the opposite direction. So we want to avoid this kind of situation. First of all, I'm going to present you a nice example of how we improved a software that had floating point round of errors that were like dangerous for the correct execution of the algorithm. So this is the case study of the ADS-B combat position reporting algorithm. So probably a lot of you are familiar with the automatic dependent surveillance broadcast technology. So this is a technology which is at the core of the next generator of air traffic management systems, and it will in the future augment the radar technology. So the idea behind ADS-B is that the aircraft periodically broadcasts information about it. For example, he broadcasts information about its position, its velocity, etc., to the nearby airplanes and to the nearby ground control stations. So this is an automatic technology, so no pilot intervention is needed. And ADS-B is mandatory from the beginning of 2020 in both the US and in Europe. However, all over the world, there are thousands of aircraft that are currently equipped with this ADS-B technology. So the pros of this technology is that it's more precise than the radar, and it provides more coverage, and it is automatic. However, when they did this technology, they decided to use an old hardware. So they have whole transponders, and the problem was that they had only 35 bits for encoding the position, like latitude and longitude of the aircraft. So if we imagine that we are gonna send like the position, like latitude and longitude in 17 bits each, we will have a granularity of more or less 300 meters for an aircraft. So you can see that this is not enough for safe navigation. So they came up with this algorithm, and that is the CPR, or Compact Position Reporting Algorithm. And the idea behind CPR is to encode in a compact way the latitude and longitude position so they can fit these 35 bits. And the main idea is that there is a translation between a coordinate that is formed by latitude and longitude, which is translated in a new coordinate system, which is the CPR coordinate system. And this system is based on the idea that we divide the whole globe into 59 or 60 equally sized zones. So you can imagine the globe, which is divided in all these equally sized squares. And each square is itself divided into at the 17 pins. So there's a mistake there in the slide. I don't know what happened. So we will have this small square, which each one is approximately of the size of 5 meters each side. And each of these bins or squares will model the possible position of the aircraft. So we will have that a CPR coordinate is the combination of a zone and a bin inside that zone. So we will have, for example, a zone number that can go from 0 to 59 or 60, and then a bin number inside the zone, which will go from 0 until 2 at the 17 minus 1. So for univocally determine the position of an aircraft, we will need the zone and the bin inside the zone. And we will get it, the position, with an accuracy of 5 meters, which is much better than 300, of course. So CPR, the CPR encoding function is very easy, and it computes the bin number. So given the latitude in this case, it will compute the bin number associated to that latitude. The same will happen for the longitude. So it will fit the CPR encoded on latitude and longitude in 17 bits, and it will also transmit beside these coordinate also if we use an odd or even encoding. So remember here that I said that you can divide the globe into 59 or 60 zones. So these are two different ways of encoding, so of dividing the Earth. So if we use a 59 encoding, the encoding is called odd. Otherwise, if we use 60 zone, the encoding is called even. So we will also transmit in our message this information, which is just 1 bit, 0 or 1. So we can combine all this information, and we will have a 35-bit long message for the position, which is other even encoding, latitude and longitude, each of 17 bits. So we have to be careful here because we are only transmitting the bin number inside the zone number here. So it's just 17 bits. So what's the deal? So for decoding the position, we will need not just the bin number, we will also need the zone number to detect where the aircraft is. So CPR has two different ways to retrieve the zone given a CPR message. So one is called local decoding. So the algorithm gets this as an input. So it has this CPR message as an input, but he knows that the aircraft not so far ago in time was at this position, latitude and longitude. So he can compute the new latitude and longitude, knowing that the aircraft wasn't that far away. And then he has another way of, in the case that there is no such previous position that is close by, CPR can use another way to retrieve the position of the aircraft, which is called global decoding. And this function uses two messages. One is sent with an odd encoding and another one with an even encoding. And it uses something that basically computes how big is the zone offset. And given how big is the zone offset, it can retrieve also in which zone the aircraft is. So this is a very high level introduction of the CPR algorithm. But one thing that we are interested in, so the important thing is that this algorithm implemented as it was at the beginning was giving a lot of trouble. So both pilots and manufacturer of the ADS-B transponders found out that it wasn't working appropriately, and this is just an example of an error that was reported by Air Services Australia, where you can see that where the aircraft was and where the CPR algorithm say it was. So this is a difference of about 500 kilometers. And of course, this is something that we want to avoid, which it can be dangerous. So when we started exploring and studying this algorithm back in 2017, the first thing that we did was, okay, let's assume that we have the possibility of reasoning with real numbers, arithmetic. So here we don't have any problems with floating point or fixed point or anything like that. So still, the algorithm wasn't behaving as expected. So the first thing that we found is that the requirements that were written for this algorithm were not strict enough. So we have proposed a slightly tiny set of requirements that, assuming real number exact arithmetic, make this algorithm working correctly. So correctly means that the difference between the original position of the aircraft, so where the aircraft is, and the position that is computed with the CPR algorithm is at most 5.1 meter, which is the position accuracy that we have. So it's how big the bin is. So we have proven with some formal tool that this new version of the algorithm with a tiny set of requirements was in fact correct. However, when we implemented this algorithm using finite precision arithmetic, we still had issues. In fact, we see here that using single precision floating point arithmetic, we found also a case study, a test case where the difference between original and decoded position was as big as 1,500 nautical miles. So the problem of this algorithm is that this algorithm uses a lot of numerically unstable functions such as the modulus or the floor. So this function have, can propagate the round of error very quickly because they are numerically unstable. So they, from a small floating point number, they can make it very big. So our solution to this problem was, first of all, well, to propose a better implementation of the CPR algorithm that uses mathematical functions that have a lower impact on the round of error accumulation, and then using a set of tools which are based on mathematics in order to verify that this implementation of CPR was in fact correct. So to do so, we used PVS, which is an interactive theorem prover. And probably most of you are not familiar with this, but an interactive theorem prover is a program that supports your proofs. So you can formalize any mathematical concept or theory inside your computer, and then you can prove a new result with the help of the computer. So this helps you to not maybe forget any corner case, and also provide an additional guarantee that your proof is in fact correct, that you didn't miss anything. And we also use a GAPA, which is a framework for the analysis of floating point programs. And also we use FRAMA-C, which is another tool which is used for checking that a C program works fine. So to give you an idea of what we did is that this in the middle is the program. So the program written in in C. And we added to this code some information in the form of a comment that in some way it models how the round of error accumulate. And we also say in this program that we require that the difference between the result of our floating point computation and the ideal real number computation must be at most half dimension of the bin number. So we have to respect the granularity of the original CPR algorithm. So this may look a little bit hard to understand, but the important thing is to understand is that we include in our C program some, what we call them, contracts. So contracts are like logic formulas that, given some hypotheses, require that some output or some other properties are satisfied. So we did this all by hand. So we wrote the code by hand using floating point numbers, and then we add this contract also by hand. And then we use these tools that are formal methods tools to prove that this implementation was in fact correct. This is an overview of the method that we used. So given our description of our algorithm, we write an improved floating point implementation of the algorithm that we check using this formal methods tool in a semi-automatic way. And we also generate this formula and these constructs that we have to prove manually with the help of an interactive theorem prover such as PBS. So this is the main idea. So the main point here, I mean, I know that it can be confusing for people who are not familiar with this kind of tools, but the main thing that I want you to understand is this process was not fully automatic at all. There was a lot of human intervention. We needed to write the code. We needed to provide the specification in a certain way. We needed to prove using an interactive theorem prover that everything was correct, etc. And all these required a certain, expertise in finite numeric application, in floating point, and in theorem prover, etc. So a lot of human intervention was needed for this. So we were successful in providing a formally verified implementation of CPR. However, a lot of human intervention was needed, and I mean, we were very happy with this work. We got that at the fixed point implementation of our algorithm, it's in fact included in the revised version of the ADSB standard. And I mean, you can check it out also online. However, what's the bad part? So as I told you, there was a lot of intervention from us, and it was a lot of work proving all this. So what we would really want as computer scientists was, just click a button and given a program, click a button and say, yes or no, is this correct? Yes or no. How big is the round of error? Everything automatic. So in the following year, we started to work on automatizing this process. And ideally, our idea was that, okay, imagine that you have a specification. So you write your program as you have real numbers. So you have infinite precision, you have exact real number arithmetic, etc. So just with a click of a button, I want you to produce an implementation of this specification using finite precision arithmetic. And I also want some formal guarantees on the round of error that may accumulate, or the problem that I may have because I represent real number in finite precision. So this led us to implement our tool that is called Precisa. And Precisa is an automatic tool that does a lot of things. So the first thing that it does is that it can compute a round of error. So a tight over approximation of the round of error that it may appear, it may accumulate in your program. And it also produces some formal guarantee that this bound is correct. This is the first thing that it does. So for example, here it's a snapshot of our tool. So given this program, we can analyze it given some initial values for the input values, and we can get a number. And this number is how different the real number program is from the floating point one. And this is all automatics. And another thing that Precisa does is to generate a floating point C implementation starting from a real number specification. And this implementation is a little bit special because it's instrumented to detect when some dangerous round of error can in some way make your program unstable. So make your program go, for example, in one execution path instead of another. But I will show this with an example. So a program, we call a program unstable when we have, for example, an if then else, like in this case, and the evaluation of the guards inside the if then else is different when we use real arithmetic and floating point arithmetic. You can see, like as in the very first example I show you at the very beginning, this may provoke a big divergence between the real and the floating point program. In this case, it's just in one branch we are going to return 1, and in the other branch we're going to return -1. So the difference here is going to be 2, which is already big, you know. So this instability, we call it, very dangerous, and we want to avoid it, and we want to know for which input this instability occurs. So this is a very simple example of what Precisa can do. So given a program, Precisa can detect which value provokes this instability, and it can graphically show it. Or it can also indicate that no instability occurs for certain input values. And another thing that we have worked on is how we can detect this instability when we are running the program. So imagine that we have this very simple example that is part of the detect and avoid library at NASA. We know this is the one that I showed at the beginning. So when floating point errors occurring in the guard, we may say to the airplane to turn right or left. So, and it may be the incorrect decision. So what we have proposed is to instrument the code to give a warning to the user when we are in certain bounds where the round of error, in fact, may provoke this wrong result. So our idea is to strengthen the guard of the if then else, taking into account the round of error that may occur, and then generate and emit a warning in the case the evaluation of the guard is different from real and floating point arithmetic. So putting this all together, what we are able to do now is, starting from a real specification of a program, assuming exact real number arithmetic, we can generate C code, which is annotated with contracts that talk about how the round of error accumulates. And we have also the option of instrumenting the code for avoiding this instability. And this C code can be input to our tool chain, and we can generate certificates in the language of PVS, which is an automatic theorem prover, that guarantee to us that this program behaves as expected, and the round of error will not exceed a certain quantity. So yeah, so at the end we have different from before. We have a new tool chain which is automatic. So we replaced the tool I showed you before with Precisa, which automatically generate the code. So for CPR we had to manually write and annotate the code. Now this job is done by Precisa in an automatic way. And then Precisa is connected to this tool that is called FromAC. And FromAC take the C code, the contracts, and generate a set of mathematical formulas that we call verification condition. So this verification condition can also be automatically discharged, automatically proven in the tool PVF with the help of automatic strategies that we have developed. So differently from before, now we have a completely automatic tool chain. So no expertise in formal method, well, a little bit of expertise in formal method maybe, but no expertise on round of error or floating point number is needed. So it's just one click of a button and you get, from a specification, you get the C code with certain guarantees on the floating point error. So we have applied this method to other NASA libraries or fragment of NASA library that implement geofencing and detect and avoid algorithms. And of course, there is much more work to do. So we are very happy that, that we have reached a point where we have an automatic generation of code and we have an automatic proof strategy that discharge our mathematical formulas. However, what we want to do next is, first of all, improve the scalability of the method. So at the moment, we cannot handle programs that are very big. So we want to improve the scalability in order to be able to generate code for entire NASA library and not just one piece at a time. And this is, for example, the NASA Daedalus library. Then we would like to use some machine. We would like to try to analyze machine learning code to see if the round of error may cause some wrong decision when machine learning technology is used. And finally, we would like to provide support for iterative structures like loops and recursion, which is still an open problem in the field. And it's very interesting when you have a loop and you want to know how big is the error at the end of the loop or how it grows. So yeah, that was all. And if you are interested in our research, you can check our GitHub repository to try out our tools. And you can also find the links to our research in my website. Thank you.
Thank you very much. Thank you very much. Are there any questions from the audience? Are there any questions from the virtual audience online? I don't. Can everybody hear me by chance?